this all going now. I do have a few things. I have a few things to say at the beginning here, which will take a bit, and give a few people the chance to join us in late, and then we'll be handing it off to John after that. But welcome, everyone. Anyone else who, welcome again to anyone who was with us yesterday, and welcome to anyone who's just joining us in. This is now our second workshop here with the first digital OAS Symposium. And this is partly because of all our amazing members who have really helped us out in putting these workshops together. We have this one tonight, and then also another one tomorrow, and then 2 on Thursday as well, all of which will be at 7:30. These sessions were kind of conceptualized in response to the Developing Professionals survey that we had sent out earlier this year, in which everyone had expressed a strong desire for more kind of skill building opportunities. I will also mention a few things here as well. For all of these events, we do request that you turn off your video and mute your mic. This just helps to minimize bandwidth and will assist with a better experience for all. For your information, tonight's presentation will be recorded. These recordings will be made available to everyone at a later date. But with that, there will be opportunities to ask questions. During the presentation, we do recommend that you type your questions into the chat, at which point one of us will get John's attention and present that question to him. Otherwise, we would recommend to wait until the end, because otherwise you will be caught potentially in the recording if you do ask them in person. But by all means, at the end, if you do want to ask it in person, that is more than fine with us. Just another quick reminder, we are still accepting entries for the photo contest that we have. And the winner for that will be getting a free green subscription to the OAS for next year. We have 5 categories, including life in COVID, vintage archaeology, and 3 others as well. But to get started now, I would like to introduce tonight's workshop presenter, John Moody. John Moody is the GIS and Digital Information Manager at TMHC, so that's Timmins Martell Heritage Consultants, an archaeological consulting firm in London, Ontario. John had participated in consulting and academic archaeological work across Canada, and he holds a PhD from Western University. He has a lifelong interest in cartography and has been playing with GIS for over 15 years now. So wherever you guys may be, I hope everyone will join me in welcoming John. So welcome, John.
Thank you. All right. So I'm going to start off by acknowledging that our symposium is taking place on traditional Indigenous territory. There are many Indigenous nations in what is now known as Ontario, and they have shaped the history of this land for thousands of years. On these lands, Indigenous peoples have developed distinct languages, customs, economies, laws, and ways of life. We want to show respect for this by acknowledging that we are on the land of the Algonquin, the Cree, Oji-Cree, Delaware, Mississauga, Ottawa, Ojibwe, Potawatomi, Haudenosaunee, Huron-Wendat, Métis, and Inuit. And since this is a GIS presentation, I thought I'd like to show everyone this website, which is a great application of GIS to things like land acknowledgements that maybe you can use in your own work. It's called Native Land. It's native-land.ca. And it is a web map that has the traditional territories of many Indigenous people around the world. So you can zoom in on this map and find wherever you are located, see the traditional territories of people who have lived there, and find additional information about those people. You will see related maps of those people, the spatial information, all sorts of great stuff. So I'd just like to point that out for anyone who's interested in that kind of thing. It's a good application of GIS to our work as archaeologists. So this workshop, I'm going to be covering sort of a few different things. Unfortunately, I can't teach you GIS in an hour. It's just impossible. There's way too much. It's way too big of a subject. So I'm going to try and point out just a few key concepts, some useful resources for archaeologists working in Ontario. And then at the end, I'm going to have some homework assignments for you guys to do sort of on your own time if you're interested in this kind of thing. So as noted in the introduction, I am a GIS manager at Timmins Martell, a consulting company in London. I've been working with GIS for about 15 years, and I've been interested in maps basically as long as I can remember. Some of my earliest memories are going on trips with my family and staring at maps of amusement parks as we drove 4 hours to PEI or something like that. So I've always, since a very early age, liked looking at maps, and now I like creating them. I started doing GIS during my undergrad during a class called Computing and Archaeology. So I just had a couple classes there, a couple lectures really, GIS. And then I've been basically self-taught since then. I've picked up projects doing consulting and my academic work. I've done some directed readings courses, but basically it's been a lot of Googling. And I encourage you, if you want to get into this, Google will become your best friend. At TMHC, I've done lots of different things like GPR surveys, developed mapping scripts with Python for our work. I've done drone photogrammetry and built in-house mapping and field databases. And I've made thousands and thousands of maps. So I do have some experience in this. This is the basic outline of the presentation. I'll be going through some very, very basic information on GIS as sort of an overview, and then digging into data and file types, software that you can use for doing GIS, some of the common tasks that I do as a GIS technician, and then finally your homework at the very end. So I'm going to start off with a poll, just to get a sense of how knowledgeable you guys are. Let's see if I can do this. So that question should pop up for you guys. I'll give you a couple minutes to answer it. I should have asked how many people are watching this instead of the election as a distraction, but. Okay, we've got 57 people reporting, so I don't know, can you guys see the results? We've got, let's see what happens when I end. We've got a range of experience. No one, not too many people have opinions about the Mercator projection, so that tells me something, but I'm glad to see that there's gonna be something for everyone in here. If you have no experience, then the beginning will be really helpful. If you have some experience with GIS, then I'm gonna give you a lot of resources for sort of moving forward. Oh, share results, there we go. All right, so let's get into it. GIS basics. Well, GIS is more than just mapping software. It's a whole constellation of software, hardware, processes, people who work doing GIS. And it's for making maps, yes, but it's also for analyzing data and displaying spatial data, and for making spatial data. With GIS, real-world variables are represented abstractly as individual layers. And these layers are combined in the GIS and analyzed or displayed. So at a very high level, that's basically what it is, a bunch of different things. To compare it with some other different technologies that you can use for making maps, it shares a lot of similarities. So you can use simple graphics editors to make maps. That's obviously still popular with a lot of people. And that is also based on the same kind of geometry. So there's still pixels involved. There's lines, polygons, points, that kind of thing. But they're all arbitrarily assessed. So there's no real world coordinates with those things. CAD is specifically for mapping or for design. So you do have geometry that is tied sometimes to real world locations, but maybe not on the other hand. And it's not really linked to other data. So within your CAD file, you will have lines of different weight or color representing different things, but there's no step beyond that to different data. So the big thing that separates GIS apart from these other technologies is that the spatial data involved is directly linked to other data, and this allows for more complex analyses. And the geometry is always tied to real-world coordinates, so you can combine different layers and make new maps. And another difference is that the data is stored outside the document. So you can take a shapefile or a JPEG that's been georeferenced and share it with someone else, and they can use it in the same way you can outside of your document. So this is what I talk about when I'm talking about data. This is just the National Topographic Service of Canada produces some shapefiles of the terrain in Canada, basically, and this is all of the data that's included with their watercourse layer. So it's really small because I had to fit it all on the screen, but there's stuff like the flow direction of the watercourse, the name in both English and French, how permanent it is, so if it's an impermanent river course or a permanent water course, all sorts of stuff, when it's made. So all of these different things can be included alongside geospatial data. In some ways, geospatial data is like looking at a spreadsheet, and the spatial data is just one column on that spreadsheet alongside a bunch of other data. You can also include things like images, or pictures, files, hyperlinks to websites, all sorts of different things. We're also concerned about metadata in GIS. So this is data about data. So it's not just having data tied to some sort of spatial geometry. There's also information included about projection and coordinate system of that geometry. There's codes, like in this table below. So this is the same information I showed on the last screen. There is a column in this shapefile called permanency, but the values are simply numeric, so 20, 59, 60. You can't really interpret that without this metadata that tells you that 59 means a permanent watercourse and a 60 means an intermittent watercourse. So this is often overlooked, but if you look at the websites where you find your data or the institutions, then you often find this kind of thing. The other important basic knowledge to sort of understand is coordinate systems and map projections. And this is very, very, very important, but it's something that I don't really think about 99% of the time that I do my work. And that's because modern GIS software makes it so you don't really need to know the coordinate systems of your files, or you won't have conflicts between different files having different coordinate systems. It's all done within the software. So it's on the fly, it's projecting from one coordinate system to another. And you won't even notice. But it's important to keep in mind because it will trip you up every now and again. So a coordinate system is a method for describing the location of places. The units are referenced against a datum, just like in archaeology. So you might have unit 200, 300 in archaeology, but it only means something with reference to a particular site datum. And it's the same in GIS. You might have 28 north, 80 west in a certain coordinate system. It might be in a different place in a different coordinate system if they're using a different datum. So latitude and longitude is probably what you're most familiar with. The units there are in degrees, so it's based on a spherical model of the Earth. UTM is another one that's very commonly used. It stands for Universal Transverse Mercator. It divides the Earth up into little slices called zones, and Ontario spans across about 4 of these zones. And hopefully with UTM, the units are in meters, so you can compare 2 UTMs and get a rough estimate of how far apart those 2 points might be. Projections are how the 3-dimensional Earth is flattened into 2 dimensions for the map. So that's shown in the image on the left here. All maps and all projections distort your geometry in some combination, so the shape, the distance, or direction might all be distorted with different projections. So you do need to pay attention at times to what projection you're using, and you need to use one that's suitable for your project. Okay. So data and file types are another huge topic that I'm only going to touch on briefly. But just overall, it's really important to keep all of your GIS data organized. And it also takes up sometimes a lot of hard drive space. Some aerial image data sets that we use are up to 20 or 30 gigabytes. So they can take up a lot of space, and you might need an extra external hard drive for that kind of thing. Another thing to keep in mind is you don't want to be moving your files around, because your GIS documents will link to those files in your hard drive. And if they move around, then your map will look broken, your data won't show up. And finally, of course, it's always important to keep backups of all of your data, just in case you mess it up or lose it. There's two main types of data that we use in GIS, raster data and vector data. I'll just describe them both separately. Raster data is a grid-based geometry, so it's rows and columns of equally sized pixels. This is just the same thing that your computer monitor is using right now to show your information. It knows that pixel X20, Y20, you need to show a white color. So it's exactly the same kind of thing. Each of these pixels is tied to usually numerical values, and usually it's 1, but it can be more. For example, an image file will have 3 bands of color, red, green, and blue. Some satellite data will have many more than that for individual slices of the visible and invisible light spectrum. It's a great data set for continuous data. So for example, aerial imagery, where there's no definite boundary between grass and trees necessarily. They might just be different shades of green. Also things like land cover, which is what that image is showing there. An important thing when you're dealing with raster data is to be aware of the resolution, so how big the pixels are. This is often in the metadata. When you look at the properties of a raster data set, it will say your pixels are 30 meters or 2 meters, and will give you a sense of how detailed that information is. Vector data, on the other hand, is point-based geometry. So it's based on X, Y coordinate pairs. And these are often joined together to create lines or polygons. Each geometry is associated with attributes. So this is like a table or a spreadsheet of data, where one column is all of the geometry in a special data type, and then multiple other columns showing different information. It's great for discrete data, because you have hard boundaries between what's your feature and what's not your feature. And be aware of scale with vector data when you're working with it, because real world features are infinitely complex. So the coastline of Canada is an infinite number. As you get more and more detailed mapping, you'll get more and more curves, and the distance will just increase exponentially. So all vector data is necessarily simplified to some degree. Rasters come in 2 types, those with no spatial information and those that have spatial information. So you can use basically any picture file you want in a GIS, but you have to supply the spatial information through something called georeferencing. And these are things like historic maps or fire insurance plans you might find online, which will not have spatial information. Other raster file types do come with spatial information, for example, a geotiff. Things like aerial imagery or landscape data or some historic maps come with this information built in. I'm just going to go through a few useful raster data sets that I use almost every day. And I think we'll be supplying this PowerPoint afterwards. So all of these yellow links are clickable. So you can go and find this data for yourself afterwards. So the Ontario GeoHub is sort of the primary place to get spatial data in Ontario. All of the ministries provide data to this one website, so you can search it and find all sorts of different stuff. There's 3 primary elevation models, or DEMs, that we use. There's a provincial digital elevation model with resolution of 5 meters, and then imagery-derived model with 2-meter resolution. And in some areas where you're particularly lucky, they do have LiDAR-derived data now, and that's available at 0.5 meter resolution, and it's really, really detailed, super great to use. Modern aerial imagery is much more difficult to come by, because it costs a lot of money to fly the airplanes to gather the high detail stuff. So there's these 5 different data sets: Swoop, Coop, GTA, OP, Drape, and Scoop. They stand for things like the Southwest Ontario Orthophotography Project. And these are flown by the provincial government. They gather these data sets and they provide them to for a cost to private individuals. If you are associated with a educational institution, however, you do have free access to this data through the Scholars Geo portal, which is another great resource. And they do have free data there as well. But if you are with the university, there's a lot of information there. Municipality and county online GISs are also a great source of imagery. Basically every government in Ontario, almost, except for some of the smaller ones, will have an online mapping portal, and you can sometimes go in there and get the imagery or data that you need. And finally, Bing Aerials is built into ArcGIS, so you can always add it to projects. For historical aerial imagery, again, you're probably going to be paying for it. The National Air Photo Library is a great resource. It costs about $50 to get an individual picture, but some of them date back to the 1930s, so they're an amazing resource. University libraries also sometimes have freely available historic aerial imagery. They restrict it to stuff prior to the copyright, so I think that's in the 1970s sometimes. So you can find lots of data from basically the 40s to the 60s. And Google is a great resource for this as well. If you just search for something like London historical imagery, there'll be sometimes lots of results for resources. There's lots of historic maps out there for Ontario. Again, we're kind of blessed that way. Dating back to the early survey plans, those are the patent plans. You can get those from the Archives of Ontario. Historic atlases and historic county maps date to the 19th century, sort of 1850s to 1890s, and those are a great resource. They have the landowners, sometimes they'll have buildings on properties, they're really high detail, and they tend to be really good quality. So really useful for historical archaeology. Finally, the historic topographic maps are available through, I think, GeoScholar as well. Excuse me. And those are the NTS and earlier map sheets produced mostly by the Canadian military. They cover most of Southern Ontario. You can get sort of scattershot what years you can get, but there's lots there for you to resource. And university libraries, finally. Again, go to the library website and search for spatial data, and usually they'll have something for you. Fire insurance plans are another really great resource for doing historical archaeology. These are really, really detailed maps, sometimes just a couple of blocks. This is in downtown London. The Library and Archives Canada has a great set of fire insurance plans, as does McMaster. There are some at Western and as well as U of T. So you can usually find the area you want, and if not, you can just use Google to find some more. They are also available in paper maps at many university libraries, those that haven't been scanned already. So you can go in there and take pictures of those yourself to use, which we have done as well. So as for vector files, the main one that you'll be coming across is the shapefile, which is sort of the most universally used. The name is a bit of a misnomer, however, because it's not just one file. When you extract a shapefile from a zip file, for example, you might have usually at least 4 different files, all with the same prefix and different suffixes. So each of these has different use. You don't have to worry about it when you're using ArcGIS or QGIS. You can it will display it as one file, so you don't have to think about these other things. But just something to keep in mind, you can't just share the .shape file with someone else because they won't be able to, there won't be any data attached to that. Geodatabase and geopackage I thought I'd mention too, because there are a couple of other vector file formats that are commonly found. For landscape data, which is sort of a broad range of things from contours, hydrology, urban areas, transportation routes, administrative boundaries, all that kind of thing. There's a few different resources you can use. If you're mapping at sort of a world or continent or country scale, then Natural Earth is a great data set. It's free to use. It's really, they've got different data sets for different scales, so I think up to 1 to 5 million. They're really high quality. They keep them up to date, so if country borders change and that kind of thing, they're constantly changing them. And they have things like, they also have rasters that show elevation for the world and that kind of thing. If you're looking at medium scale, so stuff within Canada, then CanVec is your best data source. And I showed you that table earlier is from the CanVec data. So that's the same kind of information, but just for Canada. And this actually came from the NTS map sheet set. So that was produced by the military, and after World War I, was taken over by Natural Resources Canada, became Toporama. Some of you might have used that before, but it's now called CanVec. It's a really high quality data source to use. Finally, and again, the Ontario GeoHub is a great resource for this kind of information. It can be a little bit tricky to search for stuff, but the Ontario Hydrological Network is where you're going to get your water data. The Ontario Road Network is going to have your road information, that kind of thing. Soils and geology are always important for archaeologists, and these are available. The superficial geology is on, it might be the MNR website, as well as the soil survey. So I'm just putting those links there in case anyone wants to get that. Vector data is also going to be most of your archaeological data. So find spots, archaeological sites, test units, all that kind of thing is all vector data. And that's really hard to come by. And I've got some links at the end of this presentation if you want to get some freely available stuff. But obviously, that data is highly protected. And I do have a link here to the Borden Grid, which is hosted by the BC government. Useful, just putting it up there. Moving on to software, I'm going to go over just sort of the two main choices if you're starting out doing GIS or if you're serious about doing GIS. The first is the Esri products. So this is the most widely used desktop and enterprise GIS, and it really is an enterprise level GIS. So if you go and try and purchase it, you might get a little confused because it's really geared towards companies buying it rather than individuals. It's very, very powerful and feature rich. There's all sorts of specialized programs that they include, or you can pay extra to get. So they have these two software packages. ArcMap is the older version. They've been using that for about 15 years, I guess, probably a little bit longer than that. But they're phasing it out in favor of this new program called ArcGIS Pro. As you'll notice with Esri products, if you go to their website or learn anything about them, their naming is very consistent. So everything's ArcGIS this or ArcMap that. But ArcGIS Pro is an entirely new program. It's supposed to be a lot faster, more powerful, and it's continually being updated. So ArcMap is basically at end of life. They're not really doing anything other than bug fixes for that. So if you're learning, if you want to start doing GIS, you'd probably be better off going to Pro, because that's the way sort of the industry is moving. The major downside, obviously, with Esri products is that they cost a lot of money. You can get an individual license to use ArcGIS Desktop or ArcMap. It's $150 a year for non-commercial use, but it starts at $1,500 a year for a basic license for commercial use, going up to something like almost $8,000 for one of their advanced licenses for ArcMap. So it's very costly. And you might be able to get it through your school if you're tied to a university. So QGIS is the other major software package that I was going to talk about. So the major thing about this is that it's a free program. It's open source, so people are constantly working on it, volunteers. It's probably equally as powerful as ArcMap at this point, very comparable in terms of features and abilities. It's also available for Mac and Linux as well as Windows, so it's useful for those of you who don't use Windows. And I have a link here to the download page. You probably want to get the standalone package for whatever operating system you use. There's a few different varieties, but that's sort of the base to work from. I also want to talk a little bit about web maps, because this is something I've been getting into recently. If you have any experience with HTML or JavaScript, this can be a good way to get into GIS. So I've highlighted two here, Leaflet and OpenLayers. These are JavaScript packages that you can pop into a website and make a map very, very quickly if you have the knowledge to do so. Esri also produces story maps, which is a similar kind of thing, a similar kind of web map. And Mapbox is a commercial solution for doing the same kind of thing. And that the map I showed you earlier, Native Land, that is hosted by Mapbox. So that's the kind of thing when I'm talking about web maps. That's sort of what I'm talking about. So we've reached the show and tell portion of this presentation. hopefully I didn't overwhelm you, or hopefully you got something from that first start. I'm just going to show you 3 different tasks that I do very commonly. I'm going to do them quick and dirty, sort of to give you an example of what this looks like, make you a little bit more familiar with how the software works. So the first one is just making a map, and maps are actually pretty easy to make. Anyone can make a map with any, with Photoshop or something like that. Even a person like Donald Trump Jr. can make a map if he really wants to. But we're going to go through how to make a map in ArcMap. So I'm just going to minimize this. So this is a blank ArcMap document that I just opened. This is a brand new install of ArcGIS. So this is what you'd be looking at if you wanted to make a map. Common things between ArcMap and QGIS are this layout. So in the center of the screen here, this is your data frame. This is where all your data is going to show up. Over on the left here, we've got a table of contents. So you can see it's just called layers now because we've got no data, but that's where your layers will show up. And I'm going to just start off by adding some data. All of these programs are a little bit finicky. When you're familiar with them, it's sort of second nature, but one of the hiccups that you could get with ArcMap is that it's hard to add data to begin with. So you can't just, this catalog should have a list of all of my data sources, but it's empty at this point. So I actually have to connect it to a folder on my hard drive to let it know that I have some data for it. So I'm just going to do that now. And you'll see that I have some directories here. This just mimics my folder structure in my GIS folder on my computer. So I'm going to start off by adding just a couple layers. We're going to add ORN, so that's the Ontario Roads Network. We're going to throw that in there. And as you'll see, it's going to start drawing these. There's over 600,000 roads in Ontario, so it can take a little time to load this data. Just looking for the rest of my notes. All right, so I am also going to add some water data. So this is the Ontario Hydro Network water courses and water bodies. I'm going to add the water bodies, and this is a huge file, so it's going to take a long time to load. But if I zoom in on an area, it's going to be quite a lot quicker. So I'm just panning and zooming. This is the zoom tool. There's also a pan tool, or you can use your mouse for this. And I'm going to zoom in on London, where I'm located right now, so you can see all of the roads and the river there. And as you can, maybe if you're familiar with the geography of London, you can see that this is kind of squished a little bit. So what is actually happening is this is in a projection that squishes data the further you get to the poles. So it looks great at the equator, but it's a little wonky up here in Ontario. So first thing I'm going to do is change the coordinate system by right-clicking, go into my data frame properties, and I'm going to change the coordinate system to my favorite, which is the UTM, not 83 UTM, zone 17 north. Doesn't really matter, but for this, it makes my geometry look quite a bit better. The next thing I'm going to do is to show you quickly how data is drawn. So you can see here my road segments are above my water body, and in my data frame, the roads are above the water. So this is actually my drawing order over here, as well as all of the files I'm using. So I'm just going to drop that below this one, and you'll see that the road is below the river at this point. In this case, I want them to be above it, though. So I'm just going to make like a really simple map that you maybe could make by yourself, kind of an artistic map. So first thing we're going to do is change the background because I don't want it to be white. And that's again in the data frame properties. So I'm going to go to my frame properties, make it black. There we go. Now I'm going to make my water white. Water is always white. Very easy so far. Now for my roads, I'm going to show you here. I right-clicked on it, and I'm going to look at the attribute table. So this is all of the data that's associated with each one of those roads. You can see there's things like the name of the road, which direction it goes, road class, so if it's highway, collector, that kind of thing. There's host numbers, there's all sorts of stuff. I don't really care about most of it for this, but what I'm actually interested in is the street type suffix right here. I'll show you why. Because we are going to the properties of this, and we're going to change what it looks like. So right now it's just a default color. ArcGIS has a sort of these pastel-y colors that it just assigns to things by default. So I'm going to change the symbology here. I'm going to base it on categories. So this groups features by liked attributes. And the value is the street type suffix. So there's no values here. Everything's still that pink color. And I'm just going to add all values. And what it's doing is it's going through every single row of this spreadsheet and making a note of all of the unique values. So it's going to take a second as it goes through all 600,000. I probably didn't have to wait that long, but here we go. So now we've got all of our roads, our lanes, all that kind of thing. And I'm going to pick some random colors here to show those. And then click OK to apply that. We're going to zoom out a little bit to show you what London looks like now. This is a neat little trick because over time, the way we have named streets has changed. So you can see, you don't even have to know what these colors represent, but you can see this area here, which is the older part of the city. There's lots of these blue and sort of red colored roads. So those are all streets and roads. But as you move out to the suburbs, you get all sorts of different colors because these are courts, lanes, drives, all those kinds of things. So there's a highway over here that's in blue. So this is kind of interesting to look at from a historical perspective, and it can make kind of a pretty map. So I'm going to show you the other part of this. This is all in the data frame, the data view. Both ArcGIS and QGIS have a layout view. So I'm going to click this little button down here. And this is going to show me, if I printed this off onto a piece of paper, what it would look like. So I'm just going to set up a little map here by zooming into London. And I don't want it to be that rectangular shape, so I'm going to change the properties of this data frame again. I'm going to make it square. Nice and neat. It's going to adjust that. And I have essentially a finished abstract map of London. But if I was so inclined, I could hang that on my wall maybe. And to get it out of ArcGIS, I'm just going to export it. So File, Export Map. I'm going to put it in this OAS Workshop folder. I will call it Untitled, sure. And I'm going to clip the output to the graphics extent. So instead of exporting an entire white 8.5 by 11, it's just going to export my data frame. Now we can look at that. Right here. So we have a nice finished map now. So it's very, very easy to do a simple map. You can Google all of the steps I just took. How do you change the color of a line in ArcMap? How do you add labels? How do you change the background color? All those things are very, people are asking them all the time. So if you Google just those words, you'll find the answer to that. So take that, Donald Trump Jr. It's better than yours. The second task that I find myself doing almost every day is plotting XY data. So this can be things like if you have a spreadsheet that shows site locations or a spreadsheet showing artifact locations. To get it into GIS, you can't just add the table. You have to tell it where that spatial data is in the spreadsheet, and it will do the rest by itself. But it can be a little bit tricky sometimes, just because of the assumptions that the program makes might not be the assumptions that you want it to make. So I'm going to turn this off for a second. We're still focused on London here, but I'm going to, actually, before I do this, I'm going to show you what the data looks like. I have a file here, it's called londonsites.csv. CSV is a very common file format for spatial data, or basically any data. There's no formatting, there's nothing fancy about it. So this is all of the sites sort of in London and region. And you can see there's all sorts of data here, but what we're interested in is this field here, the latitude field, and this field here, longitude. So we know there is UTM, but that's not actually separated out into eastern and northern. So we're going to stick to longitude and latitude for this example. So to add that data to our map, we're going to go File, Add Data, Add XY Data. We're going to select our spreadsheet. And ArcGIS is very helpfully looked for fields or attributes that match spatial data. So these were called longitude and latitude, so it guessed right that this is what we want. But you can also see it's got width and length here. So what it's doing is it interprets each field. Is it text information? Is it numerical information? If it's numerical information that's formatted right, it might guess that that is your X field and Y field. A Z field is for elevation, and this data set does not have that. So the other thing that's guessed is that my coordinate system is what I've used for my map. And I'll show you what happens when I add that, because we're dealing with latitude and longitude, not UTM. So my data is here. It should show up on my map as red dots, but it's not. So I'm going to right click on this and zoom to it, see where it's, okay, so I've got a bunch of sites in empty space. And if I click on this button, it will show me my whole map. Just gonna flip that off. I see, okay, so there was one dot that showed up down here. That's all of my sites. So what it's done is it's put them really close to the equator because it thinks it's UTM, but it's messed up and it's not UTM. So I'm gonna remove this, go back to London, and we're gonna add it the proper way by telling it what coordinate system to use. So we're going to select it again. And for coordinate system, there's a huge list. There's tons in here. Sometimes it's hard to guess. Sometimes you'll have to go to wherever you downloaded the data and try and find out how they've stored it. But I know for this data that I can go in here, and it is not this one. See, geographic coordinate system, North America, Canada, 983, CSRS 7. Okay, so now this is changed, and you'll see when I go back to and select this, the unit here is in degrees. So that gives us a good idea that we're talking about latitude, longitude in this case. And let's add that. So that looks good. That looks like our sites. They're in about the right location. The final thing I have to do, because this data is actually in the map document, it's not stored anywhere on my computer, so I can't share it with anyone. And I can't really query it or analyze it in any way. So I'm going to save it as a shapefile by exporting the data. All features, and we'll call it sites. Okay. And we want to add that to our map, yes. Okay, so those are in gross green color. And we're going to remove this. So it can be very, very easy to add data if it's in the right format. It can be more complicated if you don't know the coordinate system or there's other questions about the data. So another very common task, but very finicky, depending on your data. So the final thing is going to be georeferencing. Georeferencing is the process of assigning spatial data to a file. So you can use any image file for this kind of thing. In this case, I'm interested in the Fugitive Slave Chapel, which was located in downtown London. It was built in 1846, I believe, by slaves who had escaped the United States. It was still extant up to 2013, I believe, when TMHC did a project there before they moved the building to its new home. But we're looking here at a fire insurance plan of the area. We're going to georeference this fire insurance plan and see what it looks like. This is from 1907, and I got it from Western University. Okay, so first of all, we are going to add our file. It's in a different folder called FIP. And it pops up this box saying that there's no spatial information. So that's fine, we knew that, we're gonna fix that. If I do the same thing, if I zoom to this, there's nothing around it. And if you look in the corner down here, it's giving me my units. The fact that 1 is close to 0 means that I am at the equator. It's nowhere near where I want it to be. So we're gonna georeference it quickly. And I'm gonna do it quick and dirty. When I do this for work, I have to be much more careful because we're looking at individual properties rather than sort of this map level. So I'll be very precise with it. But for this instance, I'm gonna just kind of eyeball it quickly. So we're gonna add a toolbar here. These are all the different tools that ArcMap comes equipped with. There's similar kind of thing in QGIS where once you start digging into menus and toolbars, you'll see that there's a lot of tools for editing files, for working with LiDAR data, all sorts of stuff. But we're interested in this case with georeferencing. So I've got my target layer here. What we're doing is we're adding control points. So we're saying this point on my historic map is in this location in the real world. I'm gonna pop open another window here. This shows me my image that I'm gonna georeference. As I said, I'm gonna do this quick and dirty. So we're just gonna pop them in at where roads intersect. And I've got to do one thing. I need to know what roads I'm looking at. So I'm gonna turn on labels for these. Going into the properties of the roads. This is also where you add labels. We're gonna label these features with the street name. And I want it to be white so that I can see it in my black background. Great. So Thames Street is what we're looking at. Oops, daisy. Back up. So we've got Thames Street here, Thames and Bathurst, which does not exist right now. So we're gonna go with York Street, which is here. And I'm making a lot of assumptions with this. I'm assuming that the quality of my spatial data is good, that roads haven't moved since 1907. I'm assuming that the person who made the fire insurance plan did a good job. And mostly you can assume that. This is going to be wanted. And it can be tricky when landscape has changed quite a bit over time. We got Warncliffe, Stanley. We can see as we add points, it's on the fly reprojecting this data into the correct position. You can do this with as few as 2 points, but as you add more points, you'll get a more and more accurate map. I'm gonna add another one here. Find a road. Then we'll check what it looks like. So we've got 3 points, which is sort of your bare minimum. And you can see that these roads line up really well with the roads on the map. Hopefully if your connection to the stream is good enough. But this doesn't really tell us how accurate it is for things like buildings. So we're looking at 275 Thames Street, which is right here. And funny, we have an archaeological site right here. Maybe they're associated. But I'm going to double check my georeferencing before I save the data. I'm going to add a base map. So I mentioned before that ArcGIS has built in Bing imagery. This is global. It's relatively high resolution. The main problem is that it's really slow. So we're just going to let it load for a second. Okay, there we go. But I can't see what's underneath it. So I'm going to change how this fire insurance plan looks. I'm going to make it more transparent so I can see what's underneath it, see how it lines up. So I went into the properties of this I'm going to go to display this time. Again, this is not something that you could find by yourself, but there's a transparency setting here. I'm going to set it to 50%, but you could Google this information. How do I make a raster transparent on our map? And there we go. So we can see now both at the same time, and we can see our property 275 is right here. Got no building left there, but as we pan around, we can see some of these other buildings match up. It should be pretty close. Yeah, we've got one there. So we can be pretty confident that some of these buildings date to the early 20th century. If I was going to do this for work, I might pull in a parcel data, which would show individual properties. Those don't tend to change too much over time, and they're on most fire insurance plans. So over here, these are all property lines that you could use to georeference. Sometimes I also will use building corners if I know that building has stood in the same spot for that span of time. But again, this is just quick and dirty, just to show you what you'd be dealing with. So back to the slides. Just a few more advanced analyses you can do. This is a map I made for the Museum of Ontario Archaeology here in London. It's showing the density of sites, so it's similar to what I showed you before, but this has been, this is just showing the density, so that point data has been compressed into, in this case, a vector of rectangles, 1 kilometer wide, but it could be raster, to show the density of sites. And as you'll notice that they're outside the core of London, and that's because that's where archaeology has been done in the past, since the advent of commercial archaeology. Viewshed analysis is another thing that's popular with archaeologists, because basically you're asking the question, at this point, what else can I see in the landscape? So you use a digital elevation model and a point. You give it all sorts of variables like how high am I? How high is the target that I'm looking at? How far can I see? Is the earth curved, or am I pretending that the earth is flat? And it will show you which areas of the land you can see. Again, there's all sorts of assumptions in this. Are you assuming that there's no trees on the landscape? Are you assuming that your elevation data is good enough quality to get this kind of analysis correct? For example, with some of the really high resolution digital elevation data sets, they're not really useful because they show things like roads or ditches or land use changes. So they can be a little bit, they can confuse you a little bit. Least cost paths was the other one I was going to mention. So in this case, you're making a raster of how hard it is to move across a landscape. Usually this is based on a digital elevation model, because the slope of a landscape is directly proportional to how hard it is or how long it takes to move across a landscape. But you can also include things in your raster like if there's wetlands, those can be difficult to cross. Rivers can be easy or hard depending on if you have boats or not, that kind of thing. Or if it's in a dry area, that might not matter. So just something else to look into if you're interested in this kind of thing. So on to the homework section of our lecture. These are really just little tasks that I thought up that if you just want to play in GIS, this is the kind of thing that you can do. So mapping your neighborhood is super easy. I think I showed you a very basic way to do that with just road information, but you could use all sorts of things. You just add it, you symbolize it in sort of an artistic way, and then export it, and you've got yourself a nice little map. Etsy is a great place to look for inspiration. That's where I found these 3 maps. So these range from like $10 to $40, and I can make them for less if you want one. Very, very easy. You could make one for free if you wanted to. Another good way to sort of dip your toes into GIS is to contribute to OpenStreetMap, which is sort of the Google Maps, but it's open source. So you can log in, you can register, log in, and you can start editing spatial data very quickly. I mean, it has nothing to do with archaeology, but it can be a good introduction to how spatial data is stored and what kind of information you can add to it. And it can be useful for real world applications. Often when there's a disaster in places of the world where there isn't good mapping, they will have sort of a bunch of editors come in and add information to that area of the world to help with rescue or recovery efforts. And you don't need to install any fancy software with this. Finally, you can look for some archaeological data. So I've added 2 website links here There's not a lot available online, unfortunately, because it's so sensitive where archaeological sites are found. But those are sort of two open source data sets that are available. Another good way to get into this is to georeference and manually digitize maps. So you can find all sorts of gray literature on Google, just searching Archaeology Ontario or Archaeology London or something like that. Stage 3, stage 2, add those in, you might come up with some PDFs of consultant reports. And academic texts, obviously, if you have access, can be a great source of this kind of data. So finally, just a few really general resources. One's an open source textbook. If you're interested in QGIS or the Esri products, there's so much available online. There's tutorials all over YouTube. Esri has an entire training website. Lots of it's freely available, or if you buy it, it's all included in that. And then the final one is just a list that I found of tons and tons of archaeological software and resources that are freely available online. So that's it for my presentation. Hopefully I didn't overwhelm too many of you, but I'm happy to answer questions now, or you can email me if you have any questions and want some help. Thanks for coming.
Yeah, thank you. That was a absolutely fascinating presentation. But yeah, if you guys do have any questions for John, feel free to post it in the chat, or in this case, you can unmute yourself as well and ask it in person.
Did Trump lose yet? Do we know?
I think we're still pretty early in the night at the moment.